Good morning, everyone. In this talk, I present the results of a long-term effort towards landslide forecasting and specifically the design, implementation, and operation of a national early warning system for rainfall-induced landslides along the Italian railway infrastructure. Why should we care about landslides? Well, because they hit us hard. In Italy, in the last 50 years, we counted about 2,500 casualties and nearly 150,000 homeless and evacuees due to landslides. And the map shows that damaging events occur everywhere. There have been many rainfall-induced landslides on the national rail network of Italy over recent years. The 521 green dots in the map, events range in size from small washout failures to well-publicized large failures, causing major longer-term disruption. Events such as this gain high levels of media interest and negative attention. Further failures along the rail network have the potential to cause further infrastructure damage, derailment, serious injury, and even loss of life. In 2008, the Italian National Department for Civil Protection asked us this apparently simple question: can you forecast rainfall-induced landslide in an operational mode? This was a challenge. And 10 years later, in 2018, RFI, the operator of the Italian railway network, gave us the second challenge, which was to forecast rainfall-induced landslide along the national rail network. Following this request, we implemented SANF-RFI, a national landslide early warning system for the operational forecasting of the possible occurrence of rainfall-induced landslide along the RFI network. The system compares quantitative rainfall measurements, estimate, and forecast with rainfall thresholds and uses a synoptic scale landslide susceptibility zonation. The system is able to produce a new set of landslide forecasts every hour, valid for the next 24 hours. The system has many components, including landslide and rainfall data, methods and tools to define the thresholds and their uncertainties, adequate software and hardware, and criteria and tools for validation and to deliver the forecast. A key aspect is that all the components must work together. The system uses hourly rainfall measurement taken by a network of about 2,650 rain gauges, radar estimates, and numerical rainfall forecast prepared for the National Department of Civil Protection. The system uses objective and reproducible rainfall threshold defined adopting a frequency statistical method. The method assumes that the threshold is a power law curve and allows calculating thresholds at different non-exceedance probabilities. In the plot on the right, dots represent the rainfall conditions presumably responsible for the failures shown in the left map. In particular, green dots represent landslide along the rail network. Colored curves are thresholds corresponding to 5, 20, 35, and 50% non-exceedance probability levels. It means, for example, that we expect 5% of landslides below the yellow threshold. Based on the thresholds, the system determines the non-exceedance probability of landslide occurrence associated to given rainfall conditions in terms of cumulated rainfall and rainfall duration. As an example, the dots show rainfall condition of about 20 millimeters in 12 hours and 70 millimeters in 48 hours that correspond to non-exceedance probabilities of 5% and 35% respectively. We then adopt a coloring scheme to show the computed non-exceedance probability values. The system is based on a complex but yet robust infrastructure that relies on standard hardware and open source software. This was a self-imposed user requirement that makes the system portable and easier to maintain. The system can produce forecasts on rain gauge locations, interpolate grids, and on railway tracks. The violet colors indicate where, based on our forecast, we were expecting landslides. The slides show 3 standard forecasts on railway tracks prepared using measured rainfall in the previous 96 hours, rainfall forecasted for the next 24 hours, and rainfall measurements and forecasts modulated by susceptibility. In particular, in a geomorphological buffer along the rail network, we modeled a susceptibility map for slides, for rapid flows, and for rockfalls. The 3 maps were then combined in a composite map, which identified the areas with a low to very high probability of occurrence of the 3 different landslide types. So every hour for each railway tracks, the system calculates the non-exceedance probabilities for the possible occurrence of slide, of rapid flows, of rockfalls, and of the 3 combined landslide type. The slide shows standard forecasts made on the 16th of September 2022 at 4 p.m. Early on that date, flash floods triggered by heavy rainfall swept through several towns in a hilly region of central Italy, leaving 12 people dead and 1 missing. Dozens of survivors climbed onto rooftops and trees to await rescue. The system is available 24 hours a day, 7 days a week, and forecast monitoring, system maintenance, and technical support were provided in the 9 a.m. to 5 p.m. time slot, Monday through Friday, excluding holidays. A vital component of any prediction system is the validation of the system forecast. You may ask, how good is the system, and require quantitative validation metrics based on a contingency table. This is difficult to do for landslides for a simple reason. Lack of landslide information does not mean that landslides have not occurred in an area. When working at national scale, some landslides may have occurred and may have not been reported. Maybe they have occurred in non-urbanized areas. So the amount of landslide information that is lacking may be significant. So we can only be certain about 2 of the 4 cells of the contingency table, and this limits our ability to measure the performance of the system. To validate the system, we performed a hindcast by analyzing the system outputs the day before the landslides, forecasting, and the day of the landslide, nowcasting. For the purpose, we collected the information on 34 rainfall-induced landslides that occurred along the RFI network between 2018 and 2019, the orange dots in the map. For each landslide, we compiled a summary sheet containing system outputs for the day of the landslide and the day before. In the forecasting phase, we analyzed the system outputs based on the measured rainfall and forecasting rainfall 24 hours before the landslide occurrence. According to the system outputs, we were expecting a landslide only in half of the cases. In the remaining 50%, the system failed in forecasting a landslide for reasons attributable to failure of the weather forecast model, so the model predicted no rain. Inaccurate weather forecasting in space and time, so the model predicted rain, but at the wrong place or time. And finally, lack of input rainfall data. In nowcasting, we analyzed the system outputs based on the measured rainfalls 1 hour before the landslide. The system correctly predicted 88% of landslides. The remaining landslides were not predicted for 2 reasons: lack of input rainfall data, a frequent situation during severe meteorological events, and a low density of the rain gauges in the area. So the better performance during the monitoring phase highlights the importance of nowcasting, meaning the forecast on the spot that allows to follow the real-time evolution of what the model anticipates, thus reducing the margin of error between forecast and reality. The main lesson we have learned is that operational landslide forecasting of rainfall-induced landslide is possible, and we are confident it can contribute to mitigate landslide risk, reducing fatalities, but it remains a difficult and uncertain task. So a lot of work ahead of us. I just thank you, and just I want to what I've shown is the result of a team effort. So all the IRPI colleagues made this possible. Thank you.
Thank you very much for your presentation.